This is my favor to you. We stay at this level in this course. I want you to know this stuff well, but if you want to do research in this area, you got to go on. You got to get on the next bus. Today's a really important lecture. It's a continuation of what we did last time, but in detail. And I hope you take notes or at least pay attention, because it's the movie version is the editor's cut, and the editor's sometimes leaving out stuff that might be important. So, in addition to doing the slides on your own time, so please pay attention today. We're going to talk about these two paradigms in dynamic macroeconomics. We call it the macroeconomics of fluctuations, and the first paradigm is called the real business cycle paradigm, or the stochastic growth model. Last time I tried to introduce the work of Ed Prescott and Finn Kydland as sort of the driver of this. Starting in the 1980s, people started to challenge whether you really need to have a monetary sector at all to get business cycles to happen in an economy. And they took some of the interesting microeconomic innovations of the 1950s, the so-called general equilibrium theorists' work, Arrow and DeBrew, and tried to implement it into a macroeconomic framework. And that's still with us today, even though we have moved on to think of models with money and price rigidity, the fact that money matters. The second class of models kind of bases its whole methodology on the progress of the first, which is giving me the reason to talk about this to you today, which is about learning from the mistakes, or maybe the Fehltritte of your predecessors, standing on the shoulders of people who have worked very hard in their lifetimes to do macroeconomics, make progress. You learn from their mistakes. You don't reinvent the wheel. That's important in any field. It's especially true in our field. Okay, so let's summarize what we wanted to do. I'm going to review again this last period. The last lecture dealt with this stochastic difference equation as a tool that we use in our toolbox, not just a single equation, and not just a deterministic equation, but a shocked difference equation, and a system of shocked difference equations, what we call an implementation of a model. Okay, so at the end of today, certainly by the end of next week, I will have a list of equations that are shocked, and it has a dynamic of its own, and it has exactly these conditions that Slutsky was trying to invoke us to think about, and then much better in a sense than the ASAD, which is kind of a baby toy model you learn when you're an undergraduate, and because it has first principles behind it, it has microeconomic foundations. So I'm going to spend a little time reformulating, thinking again about the foundations of the stochastic growth model. You will reach back into your past and remember in October and November we talked about the Ramsey model. Then you can think of this as having its roots in the Ramsey model, but in discrete time. So instead of a continuous time formulation, which is very difficult to put stochastic around, people who do that do finance, and it's extremely difficult. It's like trying to hit a nail on the head with a sledgehammer. It's not really necessary. You don't need to do that. So macroeconomists have, because we measure in quarters anyway, or at best in quarters, sometimes in months, but most of the data that we talk about tends to be quarterly data. It makes sense to have a stochastic difference equation framework, okay? So I'm going to formulate this model. It's going to look like the Ramsey model, but it's not exactly. Very, very subtle differences, but you can think of it as an application of the Ramsey idea, and people often call the original idea Ramsey-Cass-Koopmans, and Cass and Koopmans sort of built on the shoulders of Ramsey. In a sense, the macro literature builds on their shoulders as well. So we'll start with the household, and I'll try to describe in detail why it's important to understand the microeconomics of this household, this representative household. It's a stand-in, it's a proxy for the entire behavior of the household sector, and its utility maximization problem, which looks like what Ramsey did, but Ramsey was like your planner. He was planning for you. Now you're planning for yourself. This household is thinking about its welfare. It's maximizing its expected utility. This household owns firms, and the firms also have an agenda. They have to maximize profits, and these are competitive firms. Again, this is a baseline, and I really keep this in mind. Macroeconomics is about formulating the right baseline and then moving away from it as soon as you start thinking about the real world. And a lot of people in the 1980s and 90s got lost in this perfect competitive paradigm and made recommendations based on that, which may have actually been counterproductive. So, but we still need to understand it. So we're going to have an expected utility maximization problem. It is sort of like the cornerstone. And we'll spend time in the section talking about this. Andreas will spend time talking to you about this. How to think about this. We won't use the maximum principle to solve this problem. We will use the Lagrangian function. So we'll go back to the old Lagrangian ideas, all these recurrent ideas that will help you think about macro. The firm is a little bit different. The firm is owned by the households. The households want the firms to maximize profits because the households get the profits. So it's like you're Bill Gates, you own Microsoft, you're not managing anymore, but you want Microsoft to do well because you get the profits. That's the way this model works. So the firm is going to hire capital from the household. It's going to hire labor from the household. So it's like this symbiotic, extremely incestuous relationship. But that's the way the world works. If we could all get together and live in a single household, that's the way it would look like. It would look like that. That's how it would look. Okay? We do this also for analytic convenience because it allows us to make the dynamic problem purely a household problem. It's not a firm problem in this setup. Okay, so the firms are maximizing profits period by period. We'll come back to that. Now, part of that is the shock. Remember, a shocked system of difference equations is what we want. In this RBC model, there's only one shock, and that's technology. It's the position of the production function. It's the Lagerparameter. It's the thing that's moving the production function around or setting its position in a three-dimensional space. Because a production function, think of a production function as having capital, labor, and then output. Okay? So if you can think like that, you're on your way. Okay? So the elevation off the plane is the output. And it's going to be a surface. And that surface has a concave form, or quasi-concave form. And that means that at some point, it's interesting to hire capital if you have a good run, but you're not going to hire capital forever because you're going to have diminishing marginal returns. And the same thing is true of labor. So that's what keeps the firm, even though it has constant returns to scale in both factors, it keeps it kind of in check because there's a limited amount of labor, limited willingness of workers to work, and there's a limited amount of capital at any point in time. Capital is a state variable. Okay, so these are really important. The only thing that's moving around in this model from period to period is technology. It's the position of the production function. So think of the production function, this surface is vibrating in some way, in some systematic way, but not predictable. You can try to predict it, but you're not always going to get it right. Sometimes you're going to have like iPhones, boom, the thing moves up. Or sometimes you're going to have like World War III, boom, goes down. Production function, the aggregate production function is subject to shocks. And that technology, we're going to call it, the technology shock, is the sole driver of the RBC model. Now, there are lots of variants, bells and whistles. Nowadays, you can have all sorts of clever masters and theses and dissertations that work on variations of this, but in the end, this is the baseline. Okay? So we're going to spend some time thinking about a decentralized market equilibrium in that kind of world. Okay, so households maximizing utility. Households own the firms. Firms are maximizing profits on behalf of the households. The thing is cooked such that the household does all the dynamic heavy lifting. The firm just goes period by period, maximize profits, gives the profits back to the household. So it's a nice model to understand how macro began and how it works. Because when you go on to do harder courses, harder models, you'll have to really think hard about profits. Because profits in this setup are pretty trivial. Profits are kind of not really interesting. But in a world with monopolistic competition, it is interesting. Okay, so write that down. The next part of the course, the final part of the course, when we look at Keynesian models, new Keynesian models are going to assume that firms actually set prices. They're not price takers, they're price setters, and therefore they have potential monopoly profits. And then if we have time, we'll finish this part of this agenda of solving this equation, set of equations, or this model, solving for the equilibrium of the model and looking how the model behaves in response to a shock. We're going to have to identify where the model sort of settles down. So we have to look at the steady state. We'll finish up by talking about that. Okay? So last time we looked at stochastic difference equations. We looked at the conditions for global stability. We'll see next week that this global stability condition can be softened up a little bit when you have forward-looking agents, rational expectations. A certain number of conditions can lead to a different stability concept as opposed to a global stability concept. The global stability concept says that I give this economy any endowment of capital or any endowment of other resources, it converges to a unique steady state. If it's shocked, it comes back. Okay, that's not a robust condition of all models. So we want to rule out models that have explosive, sort of exploding wave type oscillations or just waves that don't ever damp down. That doesn't sound like something we actually see in the data. But we also want to allow for agents looking forward, and we'll see that puts an extra restriction on our solution. So we'll come back to that. It's very important. So Andreas spent a lot of time investing in your knowledge of what it means to find the roots of a single equation. Single equation is just one example. An AR2 would second order difference equation can be rewritten as a vector form, a vector of order 1, and it has the same properties, etc. Then we looked at the stylized facts of economics at the short to medium run. So we're looking at cycles now, and we notice that cycles do exist. We wrote down a list of kind of stylized facts about consumption, investment, and output. The volatility of consumption is rather low, even though it's 70% or 60 to 70% of GDP in most industrial countries. It doesn't move very much, okay, and that has to do with the nature of the beast. People are consuming, and they want a smooth consumption. That's going to show up in this model today. It showed up in our model with Ramsey. The idea is to try to smooth consumption relative to investment opportunities. Investment opportunities, on the other hand, give rise to very strong fluctuations in investment spending. So the investment ratio, I divided by Y, is a very volatile number across the world. In China, Taiwan, Korea, the United States, Germany, everywhere. The business cycle is associated with lots of fluctuations of I divided by Y, and in apposition, C over Y is rather smooth, okay? So it's a stylized fact all over the world. We looked at leading indicators, lagging indicators. Employment, labor markets tend to be lagging indicators. On the other hand, financial markets tend to be leading indicators. So you see the stock market crashing like right now, likely we're going to have a recession, right? So look at the German Economic Council of Advisors, look what they're saying right now. Looks like growth is going to slow down. Where do they get that from? Well, the German stock market has been falling for the past 6 months. Okay, that's kind of a leading indicator that something's wrong. And if you follow today and next week, you'll see that that correlates a lot with the things that drive investment. So we can expect, and another good example is Turkey. I just read yesterday, Turkey's had this crash of output. Wow, not surprising. They had a huge drop in their exchange rate, but also investment has slowed down a lot. Okay, for whatever reasons, I don't want to make the comment on the politics, but it's just a fact, right? So this is a leading indicator, and therefore, these are stylized facts that any decent model has to capture. Otherwise, just throw it away, right? So then I introduced this idea of putting a random source, or you could actually put several sources of randomness in a growth model that's been discretized, and that's what we're going to call the RBC model, okay, the real business cycle. I gave you an overview, and I said these ingredients you need are kind of ingredients for any modern macro approach. So if you want to do macro nowadays, even if you have a Marxist idea, you want to put in a Marxist idea into a, and this has happened. There are a lot of serious papers that do this. You can have, two different classes in your model because now we have computers can solve these models. It's really nice. You can have a capitalist class and a workers class. And, you want to write that down. You can't just write down some equations. You got to really describe it. Okay, so you need to have preferences. The household, if there's just one household, or if it's a mixed household, if you have a working class household and a rich people's household, and if you have some impermeability between those two classes, then it could be an interesting model. But then you need to know what the people care about. Okay, the workers just want to eat, or can they save a little bit, or are they being exploited by, and it's all, I'm just talking. But in the model we're going to look at today, everyone's holding their hands together at the dinner table, and they're basically sharing everything. Okay, so that's again a specification, very robust specification of, and a clear specification of preferences. Then you have technology, what drives production possibilities? What is the supply side of the model? You can't just produce output out of thin air. You got to have a production function. So we wrote that down. We're going to go into that in detail. What kind of market form do you have? Perfect competition? Do you have imperfect competition? Do you have wage setters? Do you have wage takers as workers? Do you have labor unions? Okay, do you have monopolists charging monopolist prices? And obviously resource constraints matter. You can't just conjure up a Humboldt University to train 100,000 students. You have to build it. It takes time. It requires capital. It requires labor. Okay, so this is again, the logic is very powerful. And then finally, uncertainty. And that I put it in red because that's the new part. We didn't do that in Ramsey. Now we've got something shocking the system. Okay, so things are going well now, but hey, this year's supposed to be a bad one. Okay, maybe, people just stop using diesel cars in Germany. Ooh, that would hurt. Okay, that's a shock. That's a shock to the production possibilities of Germany. If people just drop diesel like a stone, that's a couple of million jobs, right? In terms of just doing the back of the envelope. So that's the kind of shock that people didn't anticipate in 2017, which is hitting us right now. So we can think through that using this type of paradigm. And I also mentioned that a lot of what we do in this class is based on these really powerful ideas of the 1950s, which said that under certain conditions, the decentralized market solution can actually attain the best available solution for the economy. It doesn't have to, so it's kind of like the Adam Smith theorem. As soon as you have imperfect competition, as soon as you have imperfect information, or if you have increasing returns to scale, for example, these results will break down. So this is not an FDP theorem. FDP might just believe this is true, but we economists know that maybe it's not true. Okay, maybe you don't have these perfect markets, but if they do, then we can go effortlessly between the central planner solution, Ramsey, and a decentralized market solution. That's kind of in the back of our minds as we move forward today. So there's a huge literature on this RBC model, starting with Kidler and Prescott, who got the Nobel Prize. I showed you last time. You saw the slide. Prescott wrote a nice paper in 1985, kind of in a very sort of discursive way, going into the details. There are several other papers you can look at with varying degrees of difficulty. One I'm going to post is by King and Rebelo in 1999, which is kind of the last word on this. The title of the chapter is called "Can the RBC Model Be Resuscitated?" Like it's dead and you're giving it, heart massage. So we've moved beyond that, but the methods and the techniques are still there. And a lot of the elements of the RBC model are still there. And again, the RBC model is still better in certain dimensions. I will tell you that at the very end of next lecture, it delivers predictions that are actually more in line with the stylized facts than the other models that we have. Okay. Most importantly, the strong correlation of interest rates, investment, and other macroeconomic aggregates. Okay, so again, to remind you, preferences, technology, market structure, optimal behavior. So we're assuming firms maximize profits on behalf of the households. Households are maximizing utility given their wealth, and everyone's the same, so it's a fairly straightforward problem. Okay, so keep that in mind. As soon as we start deviating from these assumptions, we're going to get into some serious heavy lifting. As soon as we have two different types of agents, for example, we have two different wealth levels. And again, this is an interesting question. Piketty wrote about this, right? He's written this huge book on capital in the 21st century. It's about the distribution of who owns the K. In this model, the ownership of K doesn't matter because there's only one owner. It's just a representative household. So in a sense, we kind of brush this distribution issue under the rug. As soon as you break it up and say, okay, we have these inseparable types, wealthy, poor, or we say there's some sort of ability to move back and forth, but it's kind of, it's random. Then we have two different households, two different problems to solve, two different wealth levels to track, and their aggregate consequences to monitor. Okay, so the model gets increasingly very complicated. So believe me, if this is my favor to you. We stay at this level in this course. I want you to know this stuff well, but if you want to do research in this area, you got to go on. You got to get on the next bus and go somewhere else, okay? The concept of a representative agent is considered to be a problem by people who look at us from the outside. I claim it is the most important simplifying assumption we can start with. It's the Robinson Crusoe assumption. Okay? And moving beyond that means, again, thinking about those implications for the distribution, which are important, no question. Most interesting research in our field today is based on that, okay? So we're going to start with a small representative agent. Think of just many of these households. They all look alike. They face the same incentives. They face the same wage because they're in the same labor market. They're hiring capital in the same capital. They're renting capital in the same capital market to firms. And the firms all face the same production function. Okay, so it's a rarefied sort of laboratory. That's what Prescott called it, a laboratory, to get the ideas right, and then you can move on. So here they are. This is what we showed last time. The lighthouse part of this model is the expected utility of the representative agent. It's an infinite sum. Okay, it's the expected infinite sum of utility in each period that gets delivered by how much you consume and how much you don't work. Okay, so think of L as the fraction of the day in work. 1 minus L is the fraction of the day you're in leisure. Okay, and this is a specialized form that has really nice properties. It has nice steady state properties. Okay, most importantly, the fraction of work in the steady state is independent of wealth in this economy. Okay, so this is a very important benchmark. There are a lot of other bells and whistles you can put on. The more general formulation has a U of C and 1 minus L. Okay, but this is, we're going to cut to the quick and think about this specialized version because it's used a lot in macroeconomic research. Okay, so write this down. It's time separable. The marginal utility of consumption in each period is independent of consumption in previous periods. That is a feature of this formulation, time separability. It's also time intra-separable, meaning that the marginal utility of consumption today is independent of the leisure I take today. So there are two types of separabilities. The first one actually rules out wealth effects of wage changes, short-term wage changes. It's going to make things very easy for us to think about. But it is not necessary to have this assumption. It just works well in the data. And this eta, this looks like an N, kind of Greek-looking N, is closely related to the Frisch elasticity of labor supply. Okay, so the size of that object, as that thing goes to zero, the Frisch labor elasticity of labor supply goes to infinity. Okay, workers are very willing to work an extra hour for the extra buck, even if it's just temporary. Okay, they don't get a whole lot of discomfort from that. Okay, as that thing goes to one, it's very uncomfortable for workers to change their work habits. Okay, so they tend to, even if there's a nice wage increase today and it's temporary, they're not going to react to it very much. And they would have a Frisch elasticity that's closer to zero. Okay, important parameter in labor because in this model, that's the only way we can get unemployment and employment to move. Okay, so you might want to write that down. The second equation is the capital equation, the capital accumulation equation. Now remember, I haven't told you yet who owns the capital, but it's obvious. It has to be the households. The households, look at this in the face. This is the evolution of the capital stock for them. There's no government in this model, and there's no taxes. You can put those in, it's been done. But capital stock tomorrow is basically a race between what I have and what I can produce and what I want to consume. Okay? And CT I can control. The household is going to choose a sequence of CT to make itself really happy. But it's got to produce that, it's got to earn that, and YT is kind of the earnings of the household. We'll show that in a second where that comes from. That comes from the sum of labor income and capital income and profit income. That's GDP. And when I say profit income, I mean excess profits. Okay, so this capital accumulation equation, I guess this went out finally, sorry about that, is the simple Goldsmith equation we had in continuous time, except it's just expressing the value of capital, the amount of capital at the beginning of t plus 1 is equal to the undepreciated capital in t plus my income minus my consumption. That's effectively my gross savings. Okay? Now that capital goes into a production function. It's essential. If you don't have capital, you can't exist. You can't produce, you can't live. So, and this is a closed economy. So capital, the capital stock, that's the stock of all the buildings, all the machines and everything else. It enters in a Cobb-Douglas way. So we're going to use a Cobb-Douglas, very specific form. If you do the readings, you'll see there's a kind of a reason for that. I can give you the short version. It delivers a lot of macroeconomic properties that look like the data in the long run. Okay, so the Cobb-Douglas form is, it's got an exponent alpha, which is the capital elasticity. It's the elasticity of output with respect to the capital stock. And here the capital stock is equal to the capital services, so we have 100% utilization in the background. We don't have variable utilization. Another trick in the toolkit of economists, you can allow people to sort of, we don't have to use this building 100% of the time. We can use it 50% of the time. What really matters is how much we use it. Okay, of course, if we don't use it, we're going to lose it. But that's depreciation. But you still, we can actually rent this place out to the Fachhochschule für Wirtschaft und Recht, and they could do their lectures in here too. Like, we could just use the hell out of it. It would cause a lot of wear and tear, right? So that's kind of what we also observe in the world. That's not in here. We have 100% utilization all the time. The households just supply the K to the firms, and the firms will use it using this production function. This function has constant returns to scale. If I double capital and double labor, given Z, I get double the output. Constant returns to scale. It will come up in a second. Okay? This is not rocket science. This is like undergraduate economics, right? Very important. It doesn't have to be, the world doesn't have to be Cobb-Douglas. You could put a CES function or all sorts of other stuff, but this is going to be very useful for us for reasons you'll see in a second. Now, ZT is this process, this one single source of randomness in our world, and we call that the technology shock. That's going to be pushing the production function around, and the agents are going to be, the household is going to be reacting to that, the firms are going to be reacting to that, and that's what's going to create wealth in the economy in a sense. When Z is high, okay, then it's opportune to work hard and produce a lot and accrete your wealth and put in some hay in the barn for a rainy day sort of thing. Okay? Boy, I'm talking like a farmer now. Is anybody listening? Okay, good. Glad to see somebody's getting my jokes. Okay, so this stochastic process, if you take logarithms of it, you get something beautiful like this. This is beautiful because it's linear in the logs. It's linear. Remember, we want linear difference equations. So ultimately, this is going to be one of our big buddies. Okay, if we can make the rest of the equations look like that, we're in business. Okay, so look at that last equation. The log of ZT is a linear function of a constant. Obviously, it's a linear function of its lagged value. Rho is the persistence of the technology shock. It's the persistence, how long it takes for the technology shock to play out. Okay, and GT is a deterministic function of time. So the notion is, like we had in those pictures, GDP per capita is kind of growing at some very, very steady rate. We want to allow that to happen in this model. We're going to take it out anyway. We're going to detrend it. We're going to get rid of that. The last part is what makes us excited, is the shock. Okay, we know what last period's technology is, and the firms can look at last period's technology. They kind of know, they get a pretty good forecast of what next period's technology is going to be, as long as rho is not equal to 0. Okay, but then this shock comes, and then suddenly we're more productive. Damn, I wish I had more capital. I would have been investing more, but I'm going to, if there's some carrying forward, maybe I'll still invest some into the future. That's the modeling of incentives of the firms in this setup. So that's a very important slide. Okay, take a good look at it. We need to define what prices and markets are, right? Ramsey didn't have prices. Ramsey was a planner. He was planning, whoever. They were planning. We still have a single good, And the good has this, it's a shmoo, it can use it for consumption or investment. If you make it into a capital good, it can help you produce, or you can put it in your mouth and chew on it. That's it. Okay, that's the level of abstraction we're going to use in this setup. I told you about the households and the firms, very important. Don't forget that. Okay, there are lots of other ways to do this, but this is a great way to teach the material. You could allow the firms to just have a crazy CEO that just wants to maximize his own wealth, right? And that'd be a different problem. Or you could have some lousy supervisory board, and the manager gets away with murder occasionally. These things are all possible, but in this model, everything is very simple. Okay? Firms are doing what households want them to do. They're maximizing profits. Think of the firm as kind of a contract between society and agents to create wealth in the economy. So we're going to have a spot market for labor services. The price is W in terms of the shmoo. So W is the real wage. So we finally see a wage in this course. Okay. Firms demand labor because they need it for production. You'll see that in a second. And they pay W to hire the labor. And I'm going real slow, but this is important. Okay. We have a spot market for capital services, and I'm not using the capital R anymore, I'm using U. Think of U as the user, to help you remember it, user cost of capital, or the user price of services. So think of this as you're a taxi driver, okay? And you have your own little company, and you supply your own labor, you hire the labor from yourself, or even better, you have a taxi company and you hire workers to work for you. You also rent the capital. You pay a fee to have this Mercedes for the day, and you put that to work driving people around. Ubermäßig. Okay? So you think about that problem, that means that you can really solidly think about the leasing price of that capital good. And this is not a violation of reality. If you think about if you look at wealth management, private wealth management, family office, that's the way it works. Nobody knows about this, that's the way it works. People own companies and they expect them to perform. That's the way it is. Even if they're publicly traded, people are large shareholders, they expect firms to, and if they don't, the firm managers get fired. That's the way it is. Okay, so now we get to the math. I'm going to write down the problem. Okay, and I'm delighted to answer this question. Yes? Yeah, it's going to be related to that intimately. I'm just using a different symbol to break you free of, I don't want you to get too confused, because we're going to look at an R later. The household is thinking about an R. The household, like, when you put your savings, the household doesn't consume, so it has the savings, and it's thinking about the R. The R is related to the U, but the R is going to have to incorporate depreciation. Okay, so the net rate of return to the household is not what the firm is going to be forking over. And the household bears the depreciation costs. That's kind of the ultimate point. Because the firms are competitive, right? Again, I'm going slowly because this is really key. This is kind of testing, maybe you've seen this before when you're an undergraduate. Let's go back to I got to talk about this. So here's this objective. This is a number. This is the expected value at period T of this expected stream of stuff. What is this stuff? It's the value of your consumption to you personally. And it's not just, now look, this is a sequence. So think of T running from 0 to infinity. I'm thinking about the next long, the long horizon here. But because I'm discounting with beta, it's not worth very much to me. What's really important is the near future. Because if beta is 0.95, go home and look at powers of beta. Look at beta to the 40th power. It gets small quickly. So we're really more concerned about the short run action. And I get utility from CT plus 1 to CT plus 2. Actually, since I'm starting at 0, it'd be C0, C1, C2, C3, C4, C5, okay? And I also get this negative utility from working. So if L is my labor supply, if L goes up, I'm gonna reduce my utility. So working hard is not so great for me. We're gonna do it if it's worth it, but let's face it, I've been sick for the past week, and actually I had a lot of fun. And I can afford to say this now at my age, but it's kind of cool to be home, just kind of poop around the house and read a book or something. Not supposed to do anything. Clean up my files, throw away some stuff. So there is value of leisure. And actually, if you have the guts to read Kittlin and Prescott, their idea was that the harder you work in their model, which is much more sophisticated, the harder you work, the more you want to take a break. Okay, so it's an intertemporal non-separability of utility over leisure. So the harder you work, you kind of get tired. God, I hate this job, and I want to take a break. Okay. The problem is their model is so powerful on that dimension, people used to make fun of it because it implies that recessions are times of spontaneous leisure, right? And we don't want to do that. That doesn't sound right because people don't like recessions. People seem not to like them. Okay, so it's in some sense it's kind of a violation of this correspondence of reality. But if you tell Prescott that, he'll still argue with you. I mean, 35 years later, he'll still fight with you about that. Okay. Now, the household is maximizing utility, this number, it's writing down a plan, not a single CT, not a single C0, it's writing down a sequence, even though it knows it's not going to actually realize that sequence in the future because new information will come forward, it's still going to have a plan. You know, have a plan? You got a plan? You got a plan? How quickly you want to get out of this school? I love this school, but I'm sure you don't love this school. You want to go out and make some money, have some fun, right? You know, you can pay for stuff, all right? So your plan is to get out of here. So these guys have a plan. Their plan is how do I do my consumption given how much stuff I have to start with, how much resources do I have, and how much can I expect to have in the future? That's exactly what this plan is about. So the solution to this in T0 is a sequence of consumption starting in 0 and going on into infinity. Okay, so it's a construct and a sequence of labor supply. How much do I want to work given what I expect is going to happen to the wage over time? Okay, so that's what makes this problem so exciting. Is we're actually, you know, we don't think people always necessarily behave like this, but this is the best. If they had an algorithm that could do it for them, this is what the algorithm would do. Okay, so in some sense, people are moving in that direction. Again, it's kind of the attainable, and it's kind of guiding our thoughts on this very interesting issue, because it does actually have some value. This is the only way the household can save, is KT plus 1. So in periods 0, the household starts with K0, and then it's got to figure out what do I do now. So if I work, I get WT times LT. And I get to choose LT. I can't choose WT because it's a price-taking model. How much capital can I supply? Well, the capital is given to me in period 0. So all I do is I get this kind of windfall of UT, but still the firms might want it or not want it. That's going to be the equilibrium. CT is what I get to choose. And pi t is what the firm pays to me in that period. And I can't influence that either because the manager's out there in Adlershof doing his stuff. Okay, and I get the money at the end of the day. So that's the hardwired competitive aspect of this problem. Okay, and this is a sequence. Okay, it's period by period. So in all t equals 0, 1, 2, 3 to infinity, you have this dynamic resource constraint or budget constraint holding. And there's no money in this economy. The currency of this model is the ownership of capital. So by, just like in Ramsey, passing the stuff forward means you, or in the OLG model, pass the stuff forward means you can consume when you're older or when you're poor. So Germany might be in great shape now, but it wasn't such great shape in 2000. So it built up its capital stock. You could think of this kind of a way of hedging our bet for the next downturn. That's kind of what happens in this model anyway. Okay. So how do we do this? How do we actually tackle this problem? How do we maximize utility? It's tricky. It requires a fair amount of intellectual energy. And because this is the basis for the future courses you'll be doing in macro, you really should invest a little bit of time. So the households are price takers, and they can do two things. And if you take my and Lutz Weinke's AMA course, you'll learn about dynamic programming, which is the rocket science version of this problem. Okay, and I say that with a bit of sarcasm because the original application of dynamic programming was in rocket science. It's how they sent rockets, into the moon, to the moon, and rockets into space. A very, very important American mathematician figured out his name was Bellman, he figured out the way to reduce this infinite dimension problem into a 2-period problem. Brilliant. Okay, that's called the Bellman equation. That's the first. So if that turns you on, if you like math, come take my course with Lutz Weinke next year. Okay, it's a kick-butt course. Okay, but again, you don't have to do that. So you can use the Lagrange approach, which just says, look, every period I got to obey this budget. I can't have more capital at the end of the period than that equation allows. Okay, so that's a constraint, but that constraint applies in every period. So it's not just one Lagrangian multiplier, it's infinite number. Every period I've got a Lagrange multiplier hitting that periodic budget constraint. Okay, it sounds like craziness, but it's actually quite simple. Okay, so you can characterize the dynamics of the equation by just looking at that Lagrange multiplier in every period. And when it's high, that means capital is really valuable. Gee, I wish I had some capital. If it's low, that means I'm swimming in capital. I don't need it. Eat some of it. It's cheap. Okay? So that's the dynamic characterization. So we're going to do the Lagrange approach for your benefit. And it's discrete, so that means there's an infinite but countable number of constraints. Everything else is completely gaga. Okay, I just love this, the fact this will be on tape for humanity, right? Because it is, it's gaga to think about. But in this setup, we have discrete number of periods. They're infinite, because it's an infinite horizon problem, but they're countable, okay? So it makes the problem really sort of, that's why macroeconomists use this setup, okay? So we don't have to do the maximum principle, all that stuff. That's really hard. And the maximum principle in with stochastic, ooh, it's going to get pretty nasty. So we're not going to do that. We still have to work to get this thing to work. We have to work to get a solution. Okay, so I'm going to write down the Lagrange function, or the Lagrangian, for the household. And again, we have to put on our thinking caps and think about what's going on in this particular setup. So we have control variables. We can control CT. And we can control CT in periods t equals 0, t equals 1, t equals 2, blah, blah, blah. We can control labor supplied, okay, L0, L1, L2, blah, blah, blah. And we also, actually, we can control the capital tomorrow, but only subject to that constraint that I just showed you, okay? So that's where the Lagrangian comes in. The Lagrangian will give me the value at the optimum of relaxing the constraint just a little tiny bit. Okay, this is a resource constraint. There's only this stuff that you can either consume or invest in every period. So that is, writing down that Lagrangian is something that I want you to learn how to do in general, not just in this particular case. I want you to be able to think about a problem that's new and write down the Lagrangian for that problem. Because once you can write down the Lagrangian correctly, you can actually solve it. You can characterize optimal behavior by looking at the first order necessary conditions for an optimum. Okay, so remember we had the Hamilton and those conditions, the Pontryagin, that was continuous time. Now we're looking at an analogous situation with discrete time. This is easier, okay? But again, you have to be comfortable with the idea of a Lagrange multiplier. So Lagrangian function is kind of a mix or a combination of two things. One is the objective you're trying to maximize, and the other thing is a function of the constraints that are holding you back. Think of yourself as trying to climb a mountain. If you were unconstrained, you would reach the top of the mountain. But suppose there's an avalanche danger. We have all these avalanches in Austria right now, and these crazy German tourists are like skiing on this, causing avalanches, and hey, why did I get killed? You don't do that. So there's a constraint. You don't ski above this level. That's a constraint. If you don't want to die, you don't ski above that constraint. So think about trying to climb a mountain, but you've got this function that defines how far you should go before you die, and you don't want to cross that line. That's kind of what we're doing in this problem. We're trying to choose the best set of CT and LT and KT plus 1, given that we cannot just create capital out of thin air. Okay, and we start with K0. These are the constraints on the problem. Good morning. Oh man, you've missed the performance of my life. So please watch the movie. She's red now, she's turning red. So Think about this. What have I done here? I've created this thing called lambda. Lambda is the Lagrange multiplier, and it's a sequence of Lagrange multipliers in each period from t equals 0 to infinity. Okay, so my first order necessary conditions will involve lambda. I'm trying to standardize the notation. Lambda was also the notation we used in the continuous case. Okay, very important. Again, I think economics lacks a certain standardization that you have in other disciplines. Okay, so this is summarizing my objective, my modified objective, my constrained objective, recognizing that in every period I have to obey the resource constraint. So the rest of the hour will be based on trying to interpret the first order necessary conditions for that problem in conjunction with the firm's optimal behavior, and the firms are owned by the households. Remember, the households own this capital, they kind of rent it to the firms, but they can't control the firms. They can only look at what happens at the end of the day, but the firms are doing the best they can. They're maximizing profits. They give the profits back to the household. You'll see in the end that the excess profits are equal to 0 in this model, so it doesn't matter, but it's important to write it down. Okay? So what are the first order conditions of a problem of this sort? It is a set of sequences of first order conditions, because it's not just CT and LT, it's LT, CT and LT for t equals 0, 1, 2, 3, 4, 5, 6 to infinity. It's a sequence of first order conditions. Every year, some of you write the answer to the problem incorrectly, and it's not good. Okay, so don't do that. This is not a simple baby optimization that you did when you were in high school. Okay, this is a sequence. And in other words, the person at t equals 0 is planning a plan, is writing down a plan that is going to control the evolution of these variables over the infinite future. And what really matters is of course the near future. So this is what the first order necessary conditions look like. I will try to characterize them in words, and I will try to describe them in economic interpretation. Okay, so here they come. Again, for t equals 0, 1, 2, 3, 4, given that the household starts with K0, the household can't just conjure up some extra K0 from Argentina or from Germany or something, okay? Just, it's there. It's a given. Very important. The first sequence of first order conditions regard consumption. Okay, so if you differentiate that Lagrangian with respect to CT for any t greater than or equal to 0, you're going to get the following condition. It looks very simple. 1 over CT is equal to lambda t. Lambda t is the Lagrange multiplier. The second condition involves optimal labor supply. Now notice that there are no other C's from other periods involved. You just have to know what lambda is. And because we have logarithmic utility, that 1 over CT is the marginal utility of consumption in period t. Okay, that's, again, we're baking this problem to be easy, and it doesn't have to be like that. And if you like this stuff, you'll accompany us into the future where you can do all sorts of crazy stuff with this model, but you'll always have this intuition. The marginal utility of consumption in each period is equal to the Lagrange multiplier on the resource constraint in that same period. Second equation, second set of sequences, the second sequence of first order conditions involves labor supply or leisure. 1 minus L is leisure, L is labor. That implies that the marginal disutility of working is equal to the value of working where the valuation is lambda. Lambda is like the utility value of getting something for work. It's the marginal utility of resources. So WT is the wage. So basically the left-hand side of this is the marginal disutility of work. Again, marginal means at the margin, not the total disutility, the marginal disutility. If I work an extra unit of time, what is it going to get me? What's it going to hurt me? And what's it going to get me? So the first part is what it does to me. It's negative, and that's going to be the marginal disutility of work. And the right-hand side is the marginal gain of that extra hour of work. Okay? Now, if you combine those first two, you can already see that we have a nice, interesting condition. Basically, we're going to have an expression for the real wage. If we can eliminate lambda, we basically have an expression for the the marginal rate of substitution of goods for leisure or for labor is equal to the real wage. That's kind of the benchmark in any setup. Again, independent of your activities in previous periods. The only thing that summarizes your activity in previous periods is this lambda, because it's going to be a function of what you've done in the past. We'll see that in a second. Okay? Because it's basically the marginal utility of wealth. And if you've been saving a lot of and accumulating a lot of wealth in the past, the marginal utility of your wealth is kind of low, according to this model. But if you don't have much wealth, it's going to be really high. All right, the third one is the most interesting of these three first order conditions. It is what Americans call the Euler equation. And if you were German, you would call it the Euler Gleichung, because the guy was Euler, this French Swiss guy. So it makes perfect sense to say whatever you want. You can call it whatever you want. It's an intertemporal dynamic optimal condition. Okay? Now look carefully what it says. It says on the left hand, it says the value of resources today in terms of utility. Think of lambda as like a utility price of resources. It's like an exchange rate. At the optimum, if you're doing the right thing, that's going to be equal to what you would be able to get if you just saved it. And what would you get if you saved it? Well, you would get this. You'd get 1 minus delta plus u, because you could rent it out in the next period. And then you'd value that rental rate, that rental increment of your income at lambda t plus 1, because it's the next period. That gives you the value and utility of this activity in the subsequent period. And you would discount that back using beta. So that would, if you're doing the right thing, you should be indifferent between that strategy or the other strategy. One strategy puts it in your mouth. That's the marginal utility of resources today. And the other is putting it into the future. So this Euler equation basically is used in finance to price assets. Robert Lucas in the 1970s and 80s actually pushed this as an asset pricing equation. So if you do finance, modern finance today, you'll apply something like this. Okay, it's kind of because you can turn it on its head. You can think of this object as being the rate of return on assets. Okay, and you could log linearize that and do all sorts of crazy stuff. Or take second order approximations and get an asset pricing equation. So macro reaches into finance. Yes. Well, if we don't consume it, we're automatically going to be lending it. Otherwise, if it's just lying around in the house, it's not worth. We kind of wasted it.
But what if they're using up depreciation exceeds the rental?
Say it again. I can't hear you.
If the depreciation of using the actives is high.
Yeah.
So that we don't get a lot of rent, so it would be worthwhile saving it as well, not using it, not decreasing.
Sure, that's part of that will be an implication of a very high value of delta. So suppose delta were really close to 1, it'd be very uninteresting to save anything because it's gone anyway. So you just and of course if you do that, you're not going to have much to produce with, so you're going to be kind of poor. That's the general implication of this equation. These are just implications of optimization. So we need to solve for the general equilibrium to get all the cross effects right. Because if you don't save anything, you're not going to have any K. And of course, the marginal product of capital, when you don't save anything, is going to be pretty high. Okay, so again, this is kind of what neoclassical, a lot of people criticize neoclassical economics. This is one of the few saving aspects, redeeming aspects of neoclassical economics. You can tell this story. Scarcity makes something more valuable. Okay, so let's proceed. The last is just to round off the question. The problem is when you do this Lagrangian exercise, you have to also differentiate the Lagrangian function with respect to the Lagrangian multiplier in every period, which just means that at an interior optimum, you're going to actually be on the resource or budget constraint in every period. So you're not going to throw stuff out the window. If you just left capital at home lying around and didn't rent it to the firms, you'd be kind of throwing it away. And that would mean that would actually mean that lambda is equal to 0. The marginal utility of having resources is 0. Who cares, right? Flush it. But we don't observe that, and you'd have to be really poor. You'd have to be very rich to be in that situation. And the utility function we put in here actually rules that out. The log utility is monotone increasing. So even if you're really rich, you still get extra utility from having a little bit more. People just are completely greedy in this model. Okay, so maybe at some point you become Warren Buffett and you want to give it to your secretary or something like that. But that's not in this model. Okay, so we've got 4 equations, and in every period we've got 4 unknowns. So we're kind of we might be in business. We're not quite there yet. We don't have a complete correspondence, but we're going to be looking at something like having n equations and n unknowns. We still have to do a little bit of work, so bear with me. We also have a cake-eating condition. So if the household really does, this household is saving and renting the capital out, the household could still be obeying these conditions and actually accumulating a lot of capital. And we want to rule that out. We want to rule out the household just accumulating capital to a point where it would make sense for it just to save a little bit less and consume it and increase its utility forever. So to rule that out, we have to have this condition. This is called a transversality condition that I'm putting up right now. Okay, so we want to rule out those cases where the capital stock grows too fast. It's a cake-eating condition. Okay, that's just a minor detail, because these equations are not sufficient to rule out that kind of behavior. It just means that I'm behaving optimally along the trajectory. I want to go to Mercury, but I might wind up going to Venus instead, or end up in the sun. Okay, so I might be obeying the first order conditions, but at some point, if I just keep on going, I'm going to land, I'm going to burn up. Okay, so that's one way of thinking about this. I mean, I love the astronomy analogies. There's some really cool ones in economics. I mean, the rocket science is just the beginning. Okay, so now we have to talk about the firms. We're not done yet, because remember, the households sell their labor to firms. They actually also own the firms, and they're just trying to squeeze value out of these firms. No distributional issues visible in this case. Okay, so but firms are kind of stupid. Firms have very little to do in this. They just have period by period. The taxi firm, they hire the capital, they hire the labor, they do the best they can, and then they give the profits to the company. They pay labor and capital, and that's it. They don't have a dynamic problem in this setup. So we've pushed all the interesting dynamics into the household, right? Okay. So households rent their labor to the firm. They sell their labor to the firm. They rent their capital to the firm, and it's all competitive. And if there is any profit, and I say that very, very intentionally, if there's any profit, because in equilibrium there will be no profit in this model, no excess profit, okay, that would be returned to the households. The households have no control. It's like a dividend, Glück gehabt or no, okay? Now I need to make a quick digression on technology. I have to talk to you about what technology is about. We know. Again, I reached back into the growth part of this course. We saw this secular growth, and we said, well, what was responsible for that growth? We had growth in the capital stock, we had growth in labor, but in fact, the economy was growing even faster. So something else was pushing the economy out. We call that technical progress. Okay. So if you just think of a constant returns production function, if f were, and this is conjunctive mood, if f were not changing, output growth over these wonderful years, also in China, would be just due to accumulation of capital and labor. So if we're stuck with this production function, the only way we can get more output is to put more capital or more labor into it. But in fact, if we have constant returns, then that's just not consistent. The economy is doing much better than the sum of the growth rates of its components. So that means we have something called technical progress. We call that, in undergrad macro, we call that the solo residual. Okay, and this is something that I don't just don't have time to teach it in the first part of the IAMA course, but it's really useful. A lot of people go to McKinsey to use this. And they go, wow, you know how to do the solo residual, okay? Because it means basically we've got this observable output growth, we've got this observable capital growth, we've got this observable labor growth. If the production function weren't changing, that thing should, this object on the right-hand side should be equal to 0. Okay, but it turns out that it's not. It turns out that every year the economy takes given capital inputs and given labor inputs and does a little bit better than it did last year. Okay, we call that technical progress. And it's really a fascinating fact. You can also look at individual companies. Most companies, when they're born, they grow fast, and the growth can be attributable to people working harder. Maybe we're investing more in equipment, but in fact, it's something else going on there. You can call that total factor productivity as well. Lots of interpretations of that. It could just be people getting used to each other. Maybe there are all sorts of new things they're learning by doing, etc. But at the aggregate level, this has a very regular behavior. And we also see that it's cyclical. It's cyclical. So Kidlin and Prescott said, wow, this must be part of the story. We have this cyclical total factor productivity. Possibly, this could be the driver of the business cycle. So I urge you all, maybe I get Andreas to give you some data, and you can do this. You just take the data for Turkey or for Germany. Real growth, that's a rate like 3%, 6%, or China, okay? What's the rate of growth of the capital stock in Turkey, Germany, or China? And what is the growth rate of labor inputs, not just people, but labor inputs, hours worked? That's the way to do it properly. A lot of times we don't have those data. And then these babies are simply weights, okay? And they look like the Cobb-Douglas exponents. Because in the Cobb-Douglas model, Cobb-Douglas production function, those are the Cobb-Douglas exponents. More generally, it's the share of capital and labor in GDP, okay? The factor income shares. So you could do this at home, impress your friends. You know, I know how to do the solar residual. You can do it for countries, you can do it for regions, you can do it for Berlin. You can do it for all sorts of, as long as you've got a geographic unit with distinguishable, measurable capital input, labor input, and output. Okay, so this is a nice exercise. And again, you can take alpha as being the Cobb-Douglas parameter. Think of it as a third. It doesn't have to be. When Solo did his 57 paper, he actually showed this is general. All you need is constant returns to scale and competitive factor remuneration. Okay? Now, if we just take 1/3 and we do this for Germany, this is what you get. Okay, you get something. So the white line is output growth, GDP growth in Germany. This is West Germany, to make this really clean. No East German stuff here. And the sort of the ochre or whatever brown line is the solar residual that I've computed. Okay? So look at that. It looks really cyclical. It goes up and booms and it goes down in recessions. And this is a fact in a lot of countries. So either it's spurious, maybe it's just some mistake we made, or it could actually have some economic content. And I think at the time, this electrified people. They said, this has got to be a part of the story, because when this thing surges, the economies tend to take off for whatever reason. Okay, so even if you have a new Keynesian view of the world, you still have to be able to explain this. Okay, it's a little bit of a challenge for us. Yeah.
Couldn't it just be that our assumptions about our production functions are just bad? I mean, if we don't have constant returns to scale, we just assume that we have
Okay.
proportional returns to scale.
Okay, so increasing returns to scale is one way of getting this result. That would mean that when the economy starts to grow, it gets more productive. Okay, so that's a good point. You could also have imperfect factor markets. So you could have monopolistic unions or monopolistic firms or monopsonistic firms. There are lots of ways to get this result. The most interesting critique at the time was that we measure capital badly. So maybe what matters is not the capital stock, but the utilization of the capital stock. So we need to ask firms, hey, what's the rate of capital utilization? And in Germany, they do that. The Bundesbank does it every month. They get a survey I think they probably get it from the EFO Institute. They survey, how much of your capacity are you using? The American Fed, every month they ask firms industrial capacity utilization figures. And those are very pro-cyclical. So properly, you'd want to adjust the capital stock for that capacity utilization and then use that result. But if you do it, you still get pro-cyclical TFP. So this is done in a naive way. I didn't do the capacity, but if you do it, you'll get a lot less of this strong correlation. So your point is well taken. Measurement error can be a problem. Okay? Let's just take what Kidlin and Prescott did at the time, and they just went to town with this. They said, okay, this is going to be the source of my fluctuations. The firm is facing this technology that's moving, and they have to somehow get ahead of it, because if ZT is up today and it's correlated, then you know it's going to be high tomorrow. So what do you want to do? You want to invest, you want to work hard, you want to hire lots of workers and produce lots. Okay, if you get a negative shock of Z, then it means it's going to be kind of lousy for the next few years. Okay, again, lots of interpretation. You can think of this as being the German auto industry, right? So suppose the diesel shock really is a shock. And I hear there are these new standards that the Volkswagen's having problems meeting right now. That's why they're producing them, and they're parking them at Schönefeld. So if you want to see something really cool, go out to Schönefeld and walk over there and see. Those cars are not people waiting to come back from Munich or Bonn, Köln-Bonn or whatever. Those are cars that VW has parked there waiting for the standards to be approved. So they're producing basically for this pile. So those kind of shocks may be persistent. And if firms know that, this is going to affect their labor demand in every period in a consistent way going forward. So this is something you have to think about. This is why the technology shock is kind of crucial. Yeah, question.
Is the picture trivial in a way? I mean, it shows just that there is something in Y that is leading to this business cycle that we see that is not capital or labor. And if we assume this, we get this correlation between Y and the TFP.
That was the response to this model, and there's a lot of discussion, and a lot of it was trying to say, have we really found something? And there is this shock element that we cannot purge. We can use lots of stuff, and if again, it's orthogonal to the information we have, to use the econometrician's terminology. Purging all the other influences that it could be, you still have this influential stuff. So even in the new Keynesian models we work with today, which we're going to get to, you still have a technology shock. We still think technology shocks matter. And there's a discussion of whether they matter the right way or the wrong way. And we know in the long run, they are the source of our welfare. So in the long run, the evolution of Z is the reason that we're sitting in a nice lecture hall and not in some dingy, dirt-covered place, right? This is kind of the evolution of our wealth over time. It's measurable. It's not clear that we necessarily know that it's always due to the same thing, but we can't ignore it. It's an elephant in the room. Okay? Notice I'm preaching to the crowds because he's got another question.
We are not sure that it's technology. It's something. Maybe a big part is technology, but it could be something else.
Sure, absolutely. Yeah. So again, I'm trying to explain. I do this because teaching these models is teaching you how economists think. Remember Joan Robinson? I told you Joan Robinson is. It's going to be on the exam. She was the lady who didn't get the Nobel Prize. Okay, and she said the reason you do this is to understand how economists think, to avoid being snowballed by economists. Okay, so that is the point, right? I'm trying to teach you why a lot of very genuine researchers, not just capitalist roaders, but people who really wanted to understand how the world works, looked at that picture and said, my God, that's incredible. And even if I do all these other regressions, I can't get rid of this cyclical bit, right? So that's what got people excited about this. And it's a great master's thesis. If you want to do this, come talk to me. It's a great that you can reconstruct. And there's a big discussion in the United States that this relationship is breaking down now. So there's Jordi Gali, one of the big thinkers in this area, in the 1990s, he has a paper where he shows that in the US, this pro-cyclicality actually starts to kind of wobble. So it's been going on since the 50s, and all of a sudden the US productivity, labor productivity in particular, seems to be moving in a counter-cyclical direction. This is not labor productivity, but it's correlated with labor productivity. Okay, so bear with me. We'll get to this. These are open questions. These are open wounds in macroeconomics, trying to figure out what this productivity is. We know it's important. We certainly know it's important for the long run. Okay, we just got to figure it out. So let's do the firm. The firm problem is trivial. Okay, this is baby economics, right? Maximize profits period by period. There's no I go to rent the taxi. I don't have to keep the taxi. I have to maintain. I have to worry about depreciation. I just rent it every day, get it, bring it back. It's kind of bumped up, and that's the depreciation. I bring it back, pay the guy, and that's it. Okay, so you basically hire labor to the point where labor is equal to the marginal product of labor in production. So you see it depends on the value of technology. When technology is high, you want workers, so you're going to pay them lots. In equilibrium, you will pay them lots. If you have lots of capital, your workers are going to be more productive. Wages are going to be higher. Okay, but if you hire lots of workers, it's going to depress marginal productivity. That's a negatively sloped labor demand curve. Okay, so that's basically lots of economics in that first equation. Same is true of the second one. So the more capital you have, the less productive it is at the margin, the less you'll be willing to pay at the margin. Its productivity is, however, also affected by this Z. So when Z is high, good times. And as long as rho is positive, rho is this, looks like a P, as long as that thing is positive, good times today means my best bet is good times tomorrow too. Okay, so now I want to show you why Euler's theorem basically tells us that profits are zero in this economy. When I say profits, I mean what happens after the firms pay capital, its rightful rental rate, U, and after workers get their wage, W. Okay, so this is something you really have to remember. This is called Euler's theorem for homogeneous functions of degree 1. And I know Andreas talked about it, because he told me. And we also talked about it in lecture, back in the growth theory days. So this is coming back to haunt you again. Important fact. Cobb-Douglas, we've cooked it to have first order homogeneity because alpha and 1 minus alpha add up to 1. If I double capital, double labor, I get double the output, holding Z constant. Z is not controllable from the firm's perspective. Okay, so if I write down the marginal product conditions for W and U, you get the following expressions. Now I can just rewrite that knowing what the production function looks like. I can eliminate K from the first condition, and I can eliminate L from the second condition. So basically, marginal product in this world is a linear function of average product. That's the magic of Cobb-Douglas. Marginal and average product of labor move in the same direction. They're proportional to each other. That's a property of Cobb-Douglas. Okay? It's a property of some other functions as well, but especially it's a simple. I can write it as a simple linear function of average product. Okay? And the same thing is true for capital. Now look at those two guys. Okay? Now if I take W and multiply it by L cancels. And if I multiply U by K, the K cancels. And if I put those two together, what do I get? I get Y. So Y is paid out to factors of production in this model. There are no excess profits. There are no big bag monopolists. Okay? Because I've cooked the model. I don't have imperfect competition in this model. Any next step would involve excess profits. We'd have to worry about it because the household gets it at the end of the period. We have to track it. Again, that's all doable, but at this level, it's important to understand that Euler's theorem and competitive markets means that the sum of factor payments in this two-factor model, capital and labor, is equal to GDP. And GDP is equal to GNP because it's a closed economy. Okay, so we're in business. This is beautiful. This is the slide to make your heart sing. Okay? Zero economic profits. Samuelson talks about economic profits versus accounting profits. Of course, the owners of the firm are happy because they get paid, they get a return. Okay, but in this world, what we care about is the excess, above and beyond the normal return to capital, the normal payment to capital. Okay, so this follows from constant returns to scale and from perfect competition. We can relax this. And we will shortly. And I think it's important because we now know in the United States that although the wage share in GDP has been constant over the decades. In the past few decades, it's starting to fall. So people are getting worried about this, saying, well, what's going on here? Do we have the wrong model? Is the production function different? Are firms dictating wages instead of taking wages? Do we have monopsony? Or are unions losing power, which they are in the United States? Could that be part of it? There are no unions in this model, but unions fight against monopsony. So once the one side falls away, firms may actually pay wages that are below marginal product. Okay? So if you like that stuff, come to my labor class. Shameless advertisement for my other courses. Okay. So, if you have a wage posting, which is non-competitive behavior, or if you have monopolistic competition, or if you have increasing, you have all sorts of reasons that we might have positive profits, but in this case we don't. So that's great. So now I'm going to take these results, I'm going to take these two equations, I'm going to eliminate W and U from the first order conditions for the household. Because if you remember, if you look back in your notes or think back, we had these first order conditions that came from the Lagrange problem. I can use when I define equilibrium, I can say firms pay marginal product of labor and marginal product of capital, and that marginal product will enter into the first order conditions in equilibrium. The firm will just, the workers behave taking that as given. So you can basically insert that into those first order conditions, and you get these nice results. Okay, so these are four equations. This is we're getting close to what we want. We want to be able to write down a log linearized set of equations that look like the difference equations from 2 weeks ago. We're still not there yet. Okay, so the first equation says marginal disutility of labor is equal to the marginal utility of consumption times the wage. And this is the wage. The numerator is the wage, and 1 over C is the marginal utility of consumption in period T. So think of this as the real wage multiplied by the exchange rate of utility for resources. The second equation is the Euler equation. It's this dynamic behavior of the optimized value of the Lagrange multiplier. If I'm doing the right thing, I want to be indifferent between moving my savings back and forth between today and tomorrow. And therefore, this puts a restriction on lambda, and lambda is just 1 over C. So this says that my marginal utility of consumption today is some function of marginal utility of consumption tomorrow times what the stuff I put into the production function tomorrow is worth to me tomorrow. So again, I'm arbitraging between the value of eating the stuff today, which is 1 over C, and the stuff of investing it in tomorrow, getting some uncertain return, because we don't know what ZT plus 1 is. We can only take an expected value of it. So this is where macroeconomics really starts rolling. You see the expectations operator here? This is a conditional expectation of the next period's product of the marginal utility of resources tomorrow plus the return of resources today put into that production process tomorrow. And this is a discounting factor because I get the utility tomorrow, I got to bring it to the present, and I use that using the beta weighting factor. Okay, so that's the Euler equation. That's a key equation, because look what it does. It expresses CT as a function of CT plus 1 in expectation. It's a nonlinear function, but it's hooking those two guys together. So macroeconomics is all about, why do we have this persistence? Why don't we live in a world of white noise? We live in a world of correlated stuff. Consumption has been great in Germany, but 15 years ago it wasn't so great. And before the unification in West Germany, it was great. It goes up and down. But the fluctuations are rather smooth compared to GDP per capita, okay, and investment. So this is kind of one way of getting our hand on that. The third equation is just the resource evolution over time. Look, it's just simply the resource constraint having plugged in and recognized the fact that GDP is equal to the sum of capital and labor income. There's no profits. That would be GDP here. So now I've cooked this thing. I've actually got 4 equations in 4 unknowns. And what else do you notice about this last set of equations? Set of sequences. Allow me to have a sip of my coffee while you think about it. What don't you see in this set of equations? We've got CT, LT, KT plus 1, and ZT. KT is given by the past, so you can't, it's a state variable, but you can choose tomorrow's. What's missing? Huh? Yeah, what happened to it? I substituted it out. I got rid of it. Good, okay? That's exactly what I wanted to hear. Lambda, you say, oh, this lambda stuff. You get rid of the lambda. Lambda is a construct. It's a Begleiterscheinung. It just kind of happens next door. You know, it's like while you're optimizing, this lambda is part of what you're doing, but you're never going to observe your lambda. I mean, I don't know what my lambda is, but it is basically a consequence of an optimization assumption, and we can eliminate it because in this particular situation, lambda t is equal to 1 over ct. Okay, so when ct is up, lambda is down. It means when I'm consuming a lot, the marginal utility of consumption is low. When I'm not consuming much, marginal utility of consumption is high. And that's a driver. That's a driver of my model. It's an endogenous driver, but it's nonetheless a driver. Yes?
That first equation, that's used lambda.
Absolutely, yeah. Yeah. Lambda is 1 over ct, so this thing alone would be the real wage in terms of the...
So that itself is telling you something about the disutility of working versus...
Yes. The first equation is called the intratemporal optimality condition, okay? It means basically, I think I even have that here. Yeah. So in the dramatic version, I would actually spool this off. So I'll do it right now. So this is the intratemporal optimality condition. This means I balance work versus the gains from work. Work makes me miserable, but I get something from it because I can use the wage to buy resources. And the real wage is given to us. Okay? So thank you for reminding me to go to the next slide. So I'm doing this now. The intertemporal optimality means that consumption today is going to stand in some relationship between expected value of a function of consumption tomorrow. Okay, so I'm going to show you tomorrow, next week that this implies, just like the Ramsey model implied, the Ramsey-Keynes model had this Ramsey-Keynes condition which said that consumption is rising when the interest rate or the marginal product of capital is high relative to your level of patience. It's the same thing. Okay, so in good times, you're going to expect consumption to be rising sharply, like in China. And in the 2000s, consumption was not rising so fast, like in Germany. This is just the intertemporal resource constraint, like I said before. And this is the dynamic process for technology. Okay, so we're almost at the end of the rope. I'm glad you asked me to. I was about to stop, and I really want to show this with the annotation next to it, because every one of these equations has an interpretation, right? Again, we're describing a household that's doing the right thing. Now, households may screw up and do the wrong thing, but if they do the right thing, they're going to be kind of hugging this set of conditions. One is involving balance of work, the work-life balance, right? You want to work hard only if it's worth it to you, and if it's not worth it to you, you're not going to work. That's exactly what the first equation says. So in times when you're not productive, the wage is going to be low, and therefore you take more leisure, work less. Upward sloping labor supply, positive Frisch elasticity. And at the same time, if you have lots of capital in your economy, you're going to have productive workers, ceteris paribus. And these are all individual equations. We can't really do that. We have to look at it as one holistic general equilibrium. That's the task for next time. I'm going to put these together. Now, if you look at that, you see that they're nonlinear. They're ugly, aren't they? They're really ugly looking. And this is a simple model. So we want to put, to get this in the form of last week, we want to approximate this model. We want to use what's called a log linearization of the model. We're going to pretend like there's a model out there that looks like this, at least locally around some steady state. And therefore, if I shock it, the local movements are like linear functions of all the other variables. So then we can use the tools that we learned last week. That's the future of macro. That's the way macro works right now. Because we're only looking at small, the business cycle is almost by definition fluctuations of 1 to 2 to 3% around a trend. So in bad cases, 3%. Usually it's like 1 or 2%. So this is the kind of thing we think we're going to try to capture with this. Okay, so next time we will write down an approximated model. First we have to identify the steady state. We have to say where's the model going to sit if I take the technology shock away and just let the model settle down, where's it going to be? That's called the steady state. And then I'm going to approximate the economy around that steady state. And that's the way we do this setup. Log linearize, and then we're gold. We're set. Okay, thanks for your attention, and I'll see you next week.